Welcome to Taylor and Maclaurin series, a way of representing with polynomials uh, many functions. A function can be represented by a Taylor series, and the way it would look is uh, f of x would be f of c plus the first derivative of f of c times x minus c. The second derivative of f of c times x minus c squared over 2 factorial, on out to the nth derivative of f of c, x minus c to the n over n factorial. So you can take a partial sum, and nobody's going to be able to deal with an infinite sum, even though it does, the bottom terms do converge to zero. You're going to want to have to do a calculation truncated somewhere. So here we can just go to the term we like and stop the series. How good of an approximation will it be? It will be converging to the value of the function. So you can look at the difference of the last two terms, and you can see how well the convergence is at that point. The remainder is to pick a z in the interval of convergence between x and c, and evaluate f at z and take the nth derivative or the n plus first derivative and multiply that by x minus c to the n plus 1 over n plus 1 factorial. So you can get a remainder, and you can check the remainder value at c. Actually in that interval, take the worst case, and you know how good your convergence is. F of x must be differentiable to all orders at c. So if we can't take the derivatives, we cannot get a Taylor series. So how does this look? Find a 5-term partial Taylor series for a cube root of x in powers of x minus 1. So f of x is the cube root of x, means f of 1 is 1. The first derivative is 1/3 x to the negative 2/3. And so if we evaluate this at x equals 1, we get 1/3. The second derivative is negative 2/3 times 1/3, or negative 2/9, x to the negative 5/3. And if we evaluate that at f of 1, we get negative 2/9. The third derivative would give me negative 5/3 times negative 2/9, which is 10/27, x to negative 8/3, and evaluating at f of 1, we get the third derivative at 1 would be 10/27. And the fourth derivative would be negative 8 times 10, negative 80, over 27 times 3, 81. X to negative 11/3. And so we evaluate at 1, we get negative 80 over 81. And now we would plug these things in. We have f of c plus 1/3 x minus 1. This is the first power. The second, x minus 2. Remember, we're going about x minus 1 is 2/9 over 2 factorial. So then at x equals 3, we got 10/27 here, 3 factorial. And then we got negative 80 over 81, 4 factorial. This one alternates in sign, positive, negative, positive, negative, positive, and it would continue on. So there is an alternation in this particular one. It is allowed, if you want everything in terms of x instead of x minus 1, it is allowed to use the binomial expansion to have the polynomial in powers of x instead of in terms of x minus 1. So to refresh the binomial expansion, the simplest thing would be to set up a Pascal triangle and go ahead and use it. The other would be to use coefficients of the combination of n things taken or at a time is the same as the binomial coefficients. Now, the Maclaurin series is like the Taylor series, except the series uses c equals 0, or we expand around 0. This one is a little bit nicer because there is a polynomial in terms of x, not in x minus c. The problem we would have had with the first example is the derivative would not have been possible. Because we would have been dividing by 0. So while it might seem that it's much easier to use c equals 0, the first example could not do so since we would have produced divisions by 0 in all of the derivatives. So the derivatives would not have existed, and that would make a big problem. A function can be represented by a Maclaurin series. That's going to look exactly the same, but instead of using c, we're going to use 0, a particular c actually. So it'll look the same, f of 0, derivative of f of 0 times x. Second derivative, f of 0 times x squared over 2 factorial, and the nth derivative, f of 0, x to the n over n factorial. And so here I'm going to say we can take the n partial derivatives just like we did a few minutes ago and end up with the number of terms we would like. The remainder looks the same. Here, 0, between 0 and x, we'll pick our z instead of between 1 and x. The last example was c and x, and we get the n plus first. Everything looks like the n plus first term except this. The function is going to be somewhere in the interval of convergence. So f of x must be differentiable to all orders of x at x equals 0. Well, we're going to have an example. We're going to look at the Maclaurin series for e to negative 2x powers of x. So if we have f of 0, it would be 1. E to the 0 power is 1. And taking the first derivative, we're going to get negative 2 times e to negative 2x, or negative 2 times 1 is negative 2. The next derivative, we'll get -2 times -2, or 4, e to the 2x. I'm sorry, e to -2x, and that would give me 4. The third derivative would give me -8 times 1 is -8, and the fourth derivative would give me 16. Plugging the values in, we get e to -2x equals 1 -2 times x plus 4 over 2 factorial times x squared minus 8 over 3 factorial times x cubed plus 16 over 4 factorial times x to the 4. So I hope you enjoyed the video, and I would ask you to subscribe to the channel if you did. And we will have other videos. In fact, we already have many other videos in calculus leading up to this, and other math topics as well. So, and if you in the physics area. So thank you.